Good morning, everyone. I think we are ready to start. Welcome to oral session 7. It's the last oral session of the main ISMIR program, but we are gonna end it strong. And thank you everyone show up after the jam session last night. I hope you all have a great time. I found many great musicians in the community. It's always a great find. Okay, so let's get started. Our first presentation will be a word-annotated paper, a Fourier explanation of AI music artifacts. It's a virtual presentation presented by Darius Afshar.
Hello, I am Darius Afshar, and this is my paper, a Fourier explanation of AI music artifacts. And this is a joint work with Gabriel Messeguer-Brocal, Camille Kesby, and Romain Henquin. So, music generative AI designates a technology that helps make music, but by that, more realistically, what they mean is that you type a prompt and you get an audio file. So this is a very streamlined process. There is not that much control in the intermediary steps. Then you're either happy and you accept the music track, or you can try to renegotiate another one by changing your prompt, which doesn't always work. So this technology has been pitched as being positive, inevitable, and democratizing music. But again, if you're a bit more realistic, this is part of the current Gen AI bubble and trend, and imbued with a corporate interest and technoliberal ideologies. But looking past these ideologies, the implementation of Gen AI is a threat for creators and real musicians in our case. And it is estimated that 24% of their revenues are at risk in the next few years. And beyond this report, it's also an issue of how they were created in the first place. Because to train their model, popular services for audio generation like Suno or Udio have scrapped copyrighted work of the artist without their consent, which is perceived by artists as a theft and led to several ongoing lawsuits. And of course, beyond the significant ecological and social impact of Gen AI, there is this AI slop invasion because, spoiler, this work has led to putting in production an AI music detector at Deezer and to displaying a label to users on album pages. And what we found was that at least 30% of daily uploads to our platform were AI generated, mostly by Suno. And on those tracks, more than 70% of streams are done by bots. So it's AI music listened to by AI, a sort of scheme to get royalties away from real human musicians. Another issue with this submersion with AI content is that they tend to misrepresent cultures, amplify biases, and propagate a very Western-centered type of cliché and stereotype on music. Just a quick point on having trained on copyrighted data, I just wanted to mention that this is not speculative, this is now acknowledged by these companies, but this is argued to fall into the fair use of data. So, which is of course one point of debate on the ongoing lawsuits, but also within the regulation that are put in place as the European AI Act. So we wanted to detect these AI music generations, which is also in line with the upcoming European AI Act on Transparency. And this is related to the topic of deepfake detection, voice spoofing, or even more largely, synthetic media forensics. But this is also a direct follow-up from a previous work we did, where we first explored AI music detection, and which was published at ICASP. Quickly, in this previous work, we found that it was easy to create a synthetic music detector with almost perfect classification score, but that these detectors were not robust to various audio manipulations. So this is what hinted us to think that there might be artifacts that are easy to detect, and we wanted to characterize what they were and to better understand why the robustness is, for instance, better on time stretching and worse on pitch shifting, or why changing the EQ doesn't affect the performances at all. So, in this paper, what we propose is a sort of theoretical analysis or an interpretability study, if you will. We wanted to ask these questions. So, what is so specific about GenAI music and generators? What do AI detectors detect, actually? What do they rely on? What are the cues? So first, to give an intuition before diving into the proof part. But of course, for the proof part, you can read the paper and we can discuss it at the poster. Okay, so in the scope of this paper, what we study is music generators that are prompt to music. So starting from a text, embedding it into a space, and then using several transpose convolution, because this is like the dominant paradigm now in machine learning, and then generating a sound that is thousands of values per second. And just to give some context on the transpose convolution, because this will be the core of our proof, many people know what this is, but you can think of it as a tiling operation. And the point we wanted to make here is that because you never learn perfectly, there are always approximation errors. If the tiler, so the transpose convolution, makes errors, what we want to put forward is that these errors will be repeated periodically. So the intuition is to say that, okay, if you have errors in your training procedures, these errors are periodical in nature. And so coming back to the context of a track, these periodicities should be present throughout the track. So that may be a way to understand the type of artifact that we have. Coming to the proof part, so first, a very useful property is to underline that a deconvolution or transpose convolution is equivalent to a zero completion between values plus a one-strided convolution. So this may be going a bit fast, but you can, of course, check the paper to have the full proof of this property and to better understand it. And then, if you implement this property within a Fourier analysis of convolutional network, which is convenient because it has many simplifying properties. For instance, a convolution in the time domain turns into a multiplication in the frequency domain. We can demonstrate, and you can check the equation later, that when you use a upsampling convolution or transpose convolution, you will replicate or periodize the spectra of what is found into these hidden layers, which can create some spiking artifacts due to the replication of the continuous component. So this is an example with the first deconvolution layer of encodec. And accumulating this artifact layers after layers into a generator, you will create this sort of spiky fractal shape in your synthetic music, which is a shape that we can predict from the architecture parameters, and very importantly, that is independent from the trained weights or the data used to train the model, which is interesting. And okay, so first what we did is then confirm these properties on real data and real generator, and sort of closing the gap between the theoretical result and what's happening when you have a lot of non-linearities and various more complex models. So we could confirm this training data and learned weight independence. And we found that looking for this spiky fractal that I was mentioning, it was super efficient to classify a music with almost perfect accuracy scores as being generated or being genuine. And doing so essentially with only a linear regression, because when you know what you're looking for, it's easy to find those. And so this was not the goal in the first place to have an accurate detector. We just wanted to interpret why there were artifacts. But along the way, we found that just finding this kind of artifact was enough to classify the AI music perfectly. But more importantly, we now have an interpretable model that is linear and a theory underlying that can be used to understand its failure cases. So that's the gist of it. And of course, there are many more unsolved problems, and of course, legal and political issues around that. The question of what if we have hybrid music between real and synthetic music? Do we detect that still? And all of that is part of the future work. Anyway, come to the poster if you're interested. So I'm not attending physically this year, but Gabrielle and Camille, or even Benjamin, my colleague, is here to answer all of your questions. I am sure that they are super fresh from the jam session from yesterday, and they will be super happy to go with you through all the mathematical proof. They are super solid on that, and I'm sure up to their top-notch performances.
Next, we have modeling the difficulty of saxophone music. It will be presented virtually by Szymon Libczycki.
Hello, my name is Szymon Libczycki, and I will be talking about how we model the difficulty of saxophone music with Jan Hayek. For musicians trying to optimize their practice, it might be useful to have difficult sections in a piece of music annotated. Additionally, it can help act as a sanity check for composers or arrangers unfamiliar with a given instrument. This difficulty analysis has been done for piano, violin, and guitar music, but not yet for woodwind instruments. I play the tenor saxophone, so I started with that, but the methodology should be applicable to any woodwind. We set out to answer the question, how hard is this to play? We created a model that can perform this difficulty annotation for us. The redder a note is, the harder the small section around it is to play. This model is largely built upon a novel dataset of recordings of trills between saxophone fingerings. We achieved this result by converting musical phrases into transition graphs between fingerings, and then working out how difficult each transition is. This allows us to find an optimal path of fingerings from which we can extract this difficulty annotation. This approach is used for modeling difficulty on other instruments as well. The difficulty of a transition is computed by taking the ratio between the required transition speed and the maximum recorded transition speed. The required speed is calculated based on the durations in the sheet music at a target tempo. The maximum speed is calculated based on extracted data from a practice-based corpus of trills we collected. These trills were collected to capture the fastest speed at which a transition can be theoretically trilled at. A similar approach has been used for designing optimal fingering sets for digital instruments. Getting this maximum transition speed value required us to record a corpus of trills between every pair of fingerings on the saxophone. We built an automatic pipeline for extracting the peak trill speed of a recording. Recording every possible pair of fingerings was quite taxing, so with expansion to more woodwinds in mind, we used a multi-layer perceptron regression model to see how well we could fill in speeds of unrecorded trills. We created regression models with 3 different encodings of the fingering pair, including expert features from saxophone pedagogy. Using the multi-layer perceptron model, we achieved a result only 8 percentage points away in mean absolute percentage error from a theoretical baseline that was calculated from variance in the data. We found that with good sampling, if using the regression model to estimate trill speeds, we only needed to actually record about 1/3 of the entire transition space to achieve similar performance. This means that models based on this approach for other similar instruments can be created with a much smaller data set. The expert features helped regression performance greatly, offsetting the low amount of data we have. Finally, non-trivial behavior was seen in the way variance behaves in the trill speed dataset. Due to multiple factors, we found that it could not be definitively stated that one recording performer was faster on every transition than another recording performer, implying that normalization and personalization of the difficulty model will not be trivial. Finally, we created a MuScore3 plugin that integrates this model on the left. The trills dataset is also publicly available on the right. Thank you for listening.
Next, we have the GemBot, a real-time system for collaborative free improvisation with music language models, presented by Lancelot Blanchard.
Hello, everyone. Thank you. Good morning. My name is Lancelot Blanchard. My co-author, Per Nasek, is in the room. And this is our first ISMIR paper. It's called the Jambot, a real-time system for collaborative free improvisation with music language models. It was made in partnership with 3 departments at MIT and our collaborators, Stephen Braid, Kimera Yelkamwazam, Jordan Rudess, Anna Huang, and Joe Paradiso. So our paper goes over the journey that we've had the immense pleasure to go through while collaborating with MIT visiting artist and Grammy-winning keyboardist Jordan Rudess. Both him and the research team were generally excited about the idea of using generative AI for live performances, and we created a musical and visual system that Jordan thought he could use to improvise with himself using models that could understand the logic and the language behind the way he improvised. And we had a concert, we presented the system at a concert in September 2024, and we called the system the Jambot. So our system uses pre-trained music language models, which, as we know, are capable of generating long sequences of symbolic music with local coherence and a compelling global arc. And in particular, we use unsupervised music transformers, which were trained on the LAC-MIDI datasets, and which auto-regressively generate tokens representing the time, duration, and pitch of each note. And we embed these decoder-only models within a multi-threaded optimized application that was developed in Juice. And we optimized the models using the Onyx runtime suite, using techniques such as 8-bit linear quantization and KV caching. So Jordan really wanted 2 things out of this system, the modeling of separate music identities, which would define the different pieces of the concert, and the implementation of controllability. And the way we answered that was through the design of different interaction strategies, which basically mean when do we prompt the model, when do we play, and how do we control the models. And it allows us to have either harmonic conditioning, melodic conditioning, or both at the same time. So I'm just going to show you a few examples, but this interaction strategy prompts the model at fixed regular time intervals, which enables the performer and the Jambot to trade and alternate in their improvisation every 2 or 4 bars, for example. And here is Jordan and the Jambot trading with the model. The second interaction strategy prompts the model on every musical gesture after a brief delay that we define as delta that enables the model to either wait for a chord to be played or for a melodic note to be held. In this example, Jordan plays chords and the Jambot improvises the melodies on top. And the third and final interaction strategy prompts the model when the performer specifically asks for it, which can be done through a specific input on the keyboard, such as like a specific range. Then we take the last K notes and we gather them to prompt the model, and this enables the performer to specifically decide when the harmonic and melodic context of the model should be refreshed. And here you can see Jordan playing leads and the Jambot improvising bass lines and chords, and you can see that Jordan refreshes the prompt by pressing root notes. So for the sake of time, I'm just going to skip through this, but you can talk to me at the poster. We crafted some training data, for the fine-tuning. It's all done by Jordan. And we also have some evaluation of the real-time system and some feedback from the audience. I'm happy to talk about this. But overall, we have a new modular system for real-time collaborative free improvisation with music language models. It relies on few interaction strategies, and we want to implement expression, responsiveness, planning, and generalization. And we really hope that more models can be run in real time for performances, so we plan to release our code on GitHub. So thank you, and come talk to us at the poster.
Thank you. Next, we have Fretboardflow, a dual model approach to optimize chord voicings on the guitar fretboard, presented by Marcel Velez-Vasquez.
Thank you for the introduction, and hello everyone who's still alive after the jam session. My name is Marcel, as mentioned, and this was joint work together with Marielle Balemans, Jonathan Driedker, and Ashley Burgoyne. Imagine you just started learning the guitar, and you come across an A minor chord, followed by a C major chord. You will probably default to the open positions like this for the A minor chord, followed by this for the C major chord. But what happens if you want to play the A minor chord somewhere else on the guitar, like this? How do you then smoothly transition to a convenient C major chord? Most beginners struggle with this, and this is the problem we try to address with the dataset and the approach we present today at ISMIR. So to start off, we built the Fretboardflow dataset. We followed the guitar set pipeline with a hexaphonic pickup, which allowed us to record every individual string of the guitar, and this in turn allowed us to disambiguate between whether the 5th fret on the A string, for example, is played versus the open D string. For the material, we drew from the McGill Billboard dataset, and we used this subset with playability annotations, so we had both high-quality chord transcriptions and a mix of easier and more difficult songs. That way, our experts could record a wide variety of voicings across a broad range of progressions. We then asked our 4 experts to record multiple convenient versions for each song in the Billboard dataset, and they practiced and recorded using our dashboard, which followed along with the audio. And the dashboard can be seen on the screen. So we worked together with 4 experts, and we recorded a total of 97 performances, ranging from 1 to 5 versions per song. And as you can see on the heat map over here of our dataset, there's a pretty smooth and equal spread across the fretboard, mostly up until the 10th fret, sometimes even reaching the 14th and 15th fret. Besides the dataset, we also propose a new model to predict convenient chord voicings, a dual model. One stream of the model encodes the chord symbols, so the valid harmonic options, and the other encodes the voicing history, the ergonomic moves a guitarist would make. Combined, they predict the next convenient voicing. And surprise, taking voicing history into account works better than only looking at the previous position. Of course, we did much more than that, and an elaborate ablation study of all the different aspects of the context history length and the different model architectures you can use for each of the dual model approaches. But if you want to know more, please visit me at the poster. We also published the dataset and the code. And next to the dataset and the code, we also implemented the camera algorithm from 2014, which allows you to delete different sources on a GitHub. And also, we plan to extend the dataset further in the future because we think more data is better in this case. Thank you for your attention.
Thank you. Next one is the Florence Prize Art Song Dataset and Piano Accompaniment Generator, presented by Tao Tao He.
Hi, my name is Tao Tao, and today I'm going to present the Florence Prize Art Song Dataset and Piano Accompaniment Generator, co-authored by Dr. Martin Melandro and Dr. Douglas Shadle. We present a dataset of 112 art songs by the composer Florence Price, the largest collection of her art songs and first digital one to be released to public. We also present a model that is fine-tuned on this dataset to create piano accompaniments in her style. First off, who is Florence Price? As you see, here's some basic information about her. But what you need to know is she is one of the most significant Black women composers in classical music, and her popularity is on the rise recently. She composed several concertos, symphonies, lots of songs for solo piano and organ, choral works, and many art songs, which are our focus today. Let's listen to one of them. This is from I Remember, one of 134 art songs by Florence Price that researchers have documented to exist. While some of them have been published, most of them only exist in the form of handwritten manuscripts stored exclusively in university archives until our project. We released the Florence Prize art song dataset, which is 112 digitally encoded art songs that we transcribed to MuseScore from her manuscripts. These 112 songs have all entered the public domain last year and are digitally available for the first time. All of these songs are for solo piano and voice. And we also annotate the songs with the lyricist, lyrics, and emotion. We released the dataset to GitHub. Let's move on to our model. Inputting a melody, it is trained to output a piano accompaniment in Price's style. We take Composer Assistant 2, a transformer model for music, symbolic music infilling, and train it on this task using our dataset. We released a collab notebook of this model. Let's hear Happy Birthday with piano accompaniment generated by our model. If you're celebrating today, happy birthday. We evaluated our model by conducting a blind test over 70 pairs of samples generated by our model and a baseline model, which we created by fine-tuning Composer Assistant 2 on the open score leader corpus, which contains over 1,000 art songs by other composers. For each pair, the subject is asked to rate which sample is better represents Price's art song accompaniment style, and we conclude that our model is capable of generating such samples. So I would like to thank my co-authors for everything on the work, and meet me on our poster. Thank you.
Thank you. Next, we have adding temporal musical controls on top of pre-trained generative models, presented by Sarah Nabi.
Thank you. Hello, everyone. I'm Sarah. I'm a PhD student at the STMS IRCAM lab in Paris. And today I'll present our work for adding temporal musical controls on pre-trained generative models. Deep generative models, such as Rave or Music to Latent, enable to perform fast, high-quality audio synthesis by directly compressing the raw waveform into a temporal latent space that captures high-level features. However, these latent representations are often difficult to interpret and highly entangled, which precludes their use as straightforward controls. Existing methods mainly rely on conditioning, adversarial regularization, or learn a prior model to condition the latent codes. However, this requires to retrain or fine-tune the large synthesis model or provide only limited types of controls. Recently, the diffusion approach proposed to add controls on pre-trained image synthesis model by directly transforming the pre-trained latent representation into a disentangled control style space using labels. They split latent features between control variables defined as independent one-dimensional Gaussian mixtures distributions and style variables supposed to capture the remaining latent features. They train a normalizing flow to learn an invertible mapping between both spaces, which enables to control image synthesis. However, this is limited to images with static attributes and relies on normalizing flow, which are known to suffer from training instability and to lack scalability. In this paper, we introduce our model Platoon to add temporal controls on top of pre-trained audio codec. We extend Platoon to time-varying musical controls by defining control variables as time-evolving Gaussian mixture distributions, and we keep style variables to model the remaining latent features. To efficiently map both temporal spaces, we adapt a rectified flow approach. Based on diffusion models and optimal transport, it learns an ODE to map observations x0 and x1 from two arbitrary distributions through straight paths. Therefore, our model learns to directly transport the control signals into its latent trajectory by directly optimizing the rectified flow training objective. This provides an invertible mapping between both spaces, and once trained, our model can be used for feature extraction, editing, and conditional synthesis. We evaluate our model on these three tasks, using both discrete and continuous controls. We benchmark on 4 datasets ranging from monophonic instruments up to full music recordings with high-level descriptors. And for instance, for melody and instrument controls, we show that our model can outperform existing baselines on the 3 tasks. While for feature extraction, it remains competitive to plugin. For the editing and synthesis task, we demonstrate strong disentanglement abilities as it remains robust to unseen combinations of attributes created by randomly swapping target controls, while maintaining the synthesis quality. However, the lower results may indicate that our model might require a minimum amount of data to be able to generalize to the 3 tasks simultaneously. For further details, please check our paper. We provide the code and audio examples on our GitHub. And so thank you, and see you at the poster sessions.
Thank you. Next, we have Quantize and Factorize, a fast yet effective unsupervised audio representation without deep learning, presented by Jae-Hoon Kim.
Hello, ISMIR. It's Jay from SiriusXM, and we are very glad to share our work titled Quantize and Factorize, a fast yet effective unsupervised audio representation without deep learning. The main motivation is that the use of foundation models on MAIA problems are gaining popularity, while their computation cost due to the deep architecture are raising concerns. Also, alternative approaches for foundation models other than deep models are severely understudied. Thus, we aim to develop a low-cost music audio foundation model performing comparatively to some of the counterparts, relying on MR features and shallow feature learners. We refer this as quantization and factorization embedding for music, QFM in short. We begin discussing the architecture of QFM. The first focus on the feature learner block. The first feature learner in each block is quantization and factorization, or QF module. For each short window of audio chunk, we calculate features such as CQT. The features can be pre-processed, such as scaling or PCA whitening, and then quantization happens per frame. Each feature vector in the chunk is mapped into integer identifiers corresponding to a cluster using k-means or Gaussian mixture model, for example. Once quantized, we apply a simple encoder to embed the ID sequence. The first processing of factorization starts with building histogram of IDs into a sparse matrix. Then each row, which represents a chunk of audio, is embedded in a continuous latent space by a pre-trained sparse factorization, such as the weighted matrix factorization. QF embeddings are later concatenated with a mean and standard deviation of features, which we call G1 module. Further, we can utilize multiple sets of features instead of one with dedicated QF blocks. In addition, we have the QF total that factorizes a concatenation of this unigram, the histogram of identifiers matrices over all feature sets, which would learn interactions among feature sets. Finally, we concatenate all intermediate embeddings and further apply robust scaling and PCA, resulting in QFM embedding for the chunk. To measure the effectiveness and efficiency of QFM, we conduct a popular downstream probing test. We include 5 feature sets, including MFCC, CQT, rhythmic, and spectral features, and finally, random 9x9 2D patches sampled from mass spectrogram. We tested various QFM setups with varying capacities and compared them with recent DIM models, including CLMR, Music FM, and Mule. We also include a baseline called G1, which is simply the concatenation of G1 embeddings from each feature set. We consider 7 downstream tasks from 5 publicly available data sets. Also, we timed the embedding computation for the audio clips from the Magna-Tegatune dataset, which is about 209 audio hours. We run the experiment on a 32-core CPU virtual machine without GPU acceleration. The results suggest that it achieves significantly better overall performance when compared to G1 and CLMR, while somewhat worse compared to Mule and Music FM. Still, we found a few tasks where QFM even slightly outperformed these models. Meanwhile, QFM turns out substantially faster in embedding computation to deep counterparts, about 7 to 10 times on CPU. Overall, QFM performs comparatively to some deep models on downstream tasks, while it trains and infers significantly faster than they do. You can actually literally do it on the laptop. For improvement, we can consider trying more features, more expressive feature learners, and bigger training set. For more details on the modeling and experimental results, check out our paper and poster. Thank you.
Thank you. Next one, we have identification and clustering of unseen ragas in Indian art music, presented by Parampreet Singh.
Hi. So hello, Sat Sri Akal, Annyeonghaseyo, ISMIR. So this is Parampreet Singh. I'm representing IIT Kanpur, and I'll be presenting my work on identification and clustering of unseen ragas in Indian art music. Okay, so what are ragas? So you might, if you listen our performance yesterday, so we sung in 2 ragas. So ragas are basically, the melodic frameworks that ragas are the melodic frameworks that guide the performances in Indian music. So basically they specify the mood or the way the performance would go. So like the first one we sung, that was a bit intense, and the second one was a bit, chill and party type. So, but there's one thing that it has been considered as a closed set problem, and like the set of ragas, it has been considered that we know all the ragas. So we try to take it one step further, and we try to treat it as a closed set. It has been treated as a closed set problem, and we try to treat it as an open set problem. So, yeah. So we use a 2-level approach. Firstly, we employ out of distribution detection to find out the ragas which are not already in the training set, and then we used an approach called novel class discovery to cluster them into new classes. Okay, so we use 2 data sets. We use Saraga and Sarvati Indian Music, our own data set. And we train on the PIM data set and test on both Saraga and PIM data set. Yeah. So the process is, we firstly extract features, like we train it in a supervised manner. So we use that as a feature extractor, and then after that, using those features, firstly we carry out of distribution detection, and on those OOD samples, we carry out clustering or novel class discovery. So for OOD, we go with a simple Monte Carlo dropout-based approach. So we already had a trained model, so we just need to perform t-stochastic passes, and with that we compute the variance, which we use for detecting the out-of-distribution classes. So higher the variance, that means the class is an OOD class. And for novel class discovery, we use loss function with 3 different components. So BC loss, which computes the pairwise, which we take between a pair of samples, and we kind of try to impose the learned information from the labeled set. And the contrastive loss, we formulate some negatives and positives based on if they are from the clips from the same audio. And then consistency loss, we perform audio transformation in volume and in time stretching, so to get the transformations. And yeah, so for OOD, we get pretty good accuracy for both data sets. And for a feature extractor, we also try like already available MERT embeddings, but we know that it is not trained for Indian ragas, so it did not perform that well, but we will definitely try the culture MERT, the paper that we saw. Maybe that will work better. And and melody-based features also, but our features proved to be better. And we tested for different clustering methods that we can discuss over a poster. And we also carried some ablation studies with different loss components. We also tested with different levels of openness, which basically defines how many unseen or seen classes are there, the ratio of that. And finally what we found that for Mishra ragas, which are the mixed ragas, it was a bit difficult to cluster, but for the simpler, like plain ragas, it was easier. So we can discuss, like the rest we can discuss on poster. Thank you.
Thank you. Next, we have MAIA, an impinting-based approach for music adversarial attacks, presented by Yushen Liu.
Hello, everyone. I'm Yushen Liu from Xi'an Jiaotong and Liverpool University, and I'm very honored to be here to present my work, MAIA, an impinting-based approach for music adversarial attack. So what is adversarial attack in music? So for a clean original music, the human beings and the machine learning model reach the agreement of the output. But if we add some small noise and some small perturbations to the input, it will lead to the model to incorrect output, while it remains the same of the perceptual of the human beings. So why we should study attack? So absolutely, we are not the attacker, and we are not aimed to compromise your machine learning model. But we want to raise the concern of the community to focus more on the robustness and the safety of your model, and to conduct the adversarial training to improve the robustness of your model. So it is also a tool to detect the alignment of the perceptual alignment with the model decision. So how to conduct adversarial attack in the music domain? So traditional LP-based adversarial attack just add some small noise to the original music. This noise is not semantic, and it is easily to compromise the perception of the music, and it is easily to be detected by human beings. So we proposed a new approach for adversarial attack based on the music imprinting. That pipeline relies on the hypothesis that is an unsafe model, usually to predict the output, just rely on some important and localized segments of the input. So we first input the music and then calculate the grid cam of the input. That map represents how important of each segment contribute to the final model prediction. So we just split them or mask them, and then reconstruct these segments according to the music imprinting generation. This created a new adversarial sample by our method. So we conduct some experiment on two MIR tasks. First is the cover sound identification, and then the music genre classification. And our results show that our method perform a good ASR and at the same time achieve a better human perception quality. So I also want to introduce some work I'm working on now. With the use of the music adversarial attacks, we can conduct a membership inference. So membership inference is to determine whether a copyrighted song was used during the training of the model without authorization. So it is quite important for artists and copyright holder. So I'm very happy to connect with you in the poster session if you are interested in my work or the membership inference. Thank you.
Thank you. Next, joint objective detection and sound source separation, presented by Sun-Yu Kim.
Hello everyone, I am Sun-Yu Kim from Seoul National University Visual Information Processing Lab, and today I present our work on joint object detection and sound source separation. This work was done together with my colleagues, which are 8 members, and the one on the right bottom side is my supervisor. And yeah. And so to start it, when we thought that human perception was fundamentally multimodal because we naturally associate visual instruments with the sound, such as, for instance, string a violin can help us isolate its sound from a mixture of several instruments. So this natural synergy between vision and audio was what inspired our research. So we focus on 2 interconnected tasks. First, object detection. We aim to localize the instruments visually in the video. And sound separation. We aim to separate the sound, determining which frequencies belong to each instrument. The reason we chose this framework was because we thought that the 2 tasks were geometrically similar because we have to identify the objects and their boundaries. So we proposed running the 2 tasks together. So, but current approaches treat these tasks like independently. They use pretrained detectors, version features, and then an independent separation network. So this 2-stage pipeline has some problems. There are no gradient flow between the 2 tasks, and visual features are not optimized for any audio objectives. And so if there's a problem with the detection module, the errors directly impact separation without any feedback. So we thought those pipelines missed the model synergies. We thought that visual information can guide better sound separation, and also sound patterns can influence object detection. So this is our research question. Can we leverage the synergy between visual detection and audio separation through end-to-end training? So we proposed F2H, which is short for G2 here. It's a unified end-to-end trainable architecture with bidirectional information flow and joint optimization of both tasks. So this is our architecture overview, and it consists of 4 components: the audio branch, the visual branch, the audio visual branch, and finally a spectrogram decoder. So the audio branch is based on the pre-trained audio spectrogram transformer, which is known to perform well on many tasks, and the visual branch uses a DTR-based object detector. So we combine the 2 branches in an audio fusion module, and we also use a dynamic filtering mechanism which selects relevant object queries. It removes low confidence or overlapping detections and the features associated to them. And this prevents confusion from spurious regions, confusing the fusion module. So the fusion module is a cross transformer with cross attention. It fuses object queries with audio tokens, and the spectrogram decoder finally is conditioned on those fused features, and it generates masks for each detected object. Our detection loss is based on the DETF, Hungarian algorithm-based set matching loss, and our separation loss is the L1 loss between the ground truth masks and the predicted masks. So we optimize these two objectives together. And so this allows the gradients from both tasks to propagate into both branches. So our experiments show that on the music and music 21 benchmarks, we achieved the state-of-the-art performance. If you look at the table, you can see that we perform about 1 or 2 decibels better than the previous SOTA method, iQuery. And I don't have the audio now, but these are the qualitative examples. On the left, you can see that the detection is quite accurate, and also the spectrogram has minimal interference compared to other models. So we conducted ablation studies, and we found that the bounding box filtering was important, and also the using a transformer was compared much better than using a unit-like decoder. Also, cross-attention and object detection guidance was important for sound separation. So in conclusion, we found that the end-to-end optimization between object detection and sound separation enables cross-task learning, and more concretely, dynamic filtering is crucial for performance, and cross-attention performs concatenation, and the joint training is mutually beneficial. And so our hypothesis that the two tasks are semantically related and can learn a joint embedding space was verified. And thank you for listening, and if you have any questions, please ask me in the poster session.
Thank you. Next, we have user-guided generative source separation, presented by Yutong Wen.
Hi everyone, my name is Yutong, and it's happy to present my source separation work collaborated with my professors Minjie and Paris. So in separation, traditional VBDO setup separates a mixture into 4 fixed stems: the vocals, bass, drums, and others, but they do not support extraction of arbitrary instruments. So a natural question to raise is that, can we come up with a universal condition so that we can just separate whatever we want? And here's what we propose. Let's have an example first. Where's my mouse? Here's a mixture. And suppose I want to extract the source that goes like, where's my mouse? Sorry. Yeah, sorry. Okay, so I hum over the source that I want to extract, and the model will output. Sorry. Great. Okay, so finally, so we propose a conditional source extraction framework that takes 2 forms of conditions. First is mimicry, which is just what I demonstrated, and users can just hum or play any instruments over the target source melody to extract the source. And the second form of condition is the masking on the MEL spectrogram. We noticed that a lot of musicians have background knowledge about the spectrogram representation of audio. So now, in order to separate a source, you can just directly draw a mask onto the MEL spectrogram to highlight the regions where the source might appear. And we implement this using a diffusion model. And here's our proposed model overview. We design a twin unit architecture where the main score unit is responsible for the generative part, and the conditional branch is responsible for all the necessary conditions for separation. And for the training data, of course, we need the target source plus the background music for normal source separation. But here, what's more important is that we need to match the user input to the target source. However, there's just no such data set that comes with aligned mimicry from users. So we need to curate the data on our own. And we do this by leveraging a MIDI waveform aligned data set, and we simulate the mimicry from the MIDI data. Here's one example. So here's a piece from the data set, and on the left is its corresponding MIDI. And we can synthesize from this MIDI to get the mimicry. Well, I know everyone's going to ask why this doesn't sound exactly aligned to the MIDI data. And this is because we want to simulate the real user input where nobody can hum or play instrument perfectly following the target source. And we do this by applying a bunch of augmentations to the MIDI data. And finally, we synthesize the MEL mask by applying Gaussian filters to the ground truth spectrogram. And here's some boring numbers. So we show results on the SDR, and we compare to mask prediction baselines. And we group the instruments into 10 categories, and our model achieved an overall 10.46 dB SDR. We further conducted subjective evaluations. In the first section, we assessed the separation quality. We see that the result shows that our model reaches a score very close to the ground truth and outperforms the baseline. And we'll also move on to conduct another task, which is the timbre preservation task. This is because we know that diffusion models are known to predict audio with a timbre shift, especially under separation task or enhancement task. But still, our result shows that we can have better score than the baseline model. And this highlights the advantages of using generative modeling. Let's talk about more details in my poster session. Thank you so much.
Thank you. Next, we have leveraging Carnatic live recordings for singing voice separation using regression-guided latent diffusion, presented by Janice Ragas.
Thanks. So, well, yeah, hello everyone. This is Janice, trying once more to leveraging Carnatic live recordings for singing voice separation for Carnatic music, this time using generative models. So, well, this work is motivated by the relevance of the singing voice for the computational analysis of Carnatic music, and therefore the separation of it for further analysis. But we still observe that open models trained on open datasets still struggle to generalize properly to Carnatic music, mostly given, the idiosyncratic instrumentation and singing techniques, and this stereophonic nature with a strong source overlap. So multi-stem Carnatic recordings that are clean are scarce and are very difficult to record because, this is a repertoire that is mostly enjoyed live and it's highly improvisational. But what we observe in the literature is that we have large quantities of live multi-stem recordings that are recorded from live performances. And that is great because we can record large quantities of that. But it has a drawback, and that is that, microphones for individual instruments pick up interferences from the rest of the sources, room acoustics, acoustic noises, and so on. However, being able to leverage the domain knowledge in this data for a task of separation would be really great. And this time we're going to try to achieve that using generative modeling. So the research question of this work is, can we train a generative model based on latent diffusion that can generate vocals with bleeding or background interferences corresponding on the conditioning on the corresponding mixture, And then if that is possible, can we just go a little bit further and improve a little bit more the result, leveraging the flexibility of these systems, but without relying on any in-domain clean data. So the idea is to train the separator network only with Carnatic multi-stem recordings from live performances, and then try to go a little bit further without relying on any clean in-domain multi-stem data. So we work on a latent diffusion unit that operates on music-to-latent codes, and most importantly, we design a convolutional network that we call the bleeding predictor, and that is basically in charge of predicting the amount or the ratio of interferences that we have in a vocal signal, right? So if we have a full mixture, we would like to predict a value of 1, which is maximum interference. If we are having a singing voice alone signal, we would like to predict 0. And then we would have a floating point for all the ratios in the middle, right? And this is trained with non-Carnatic data in a synthesized interference data set. So we begin by pre-training the separator latent diffusion unit by injecting the mixture as conditioning and trying to reconstruct the signal, but trying to lower down the whole Carnatic accompaniment to, background interference. And after some training epochs, we will do a small fine-tuning stage in which we use the bleeding ratio predicted using the pre-trained bleeding predictor as a penalization term, trying to punish, so to say, the network when it's generating too much bleeding in the signals, right? And most importantly, what we further try to do is to perform bleeding guidance. So one thing that we do is during sampling, we compute at each sampling step of the latent diffusion model the amount of bleeding in the signal. We then compute the gradient toward 0 bleeding, and we then steer this gradient to push the generation trajectory toward an area with a little bit less bleeding or even really low bleeding. Well, we evaluate the bleeding predictor separately and to see how it generalizes to Carnatic and to live music. And again, bunch of boring numbers. Come to see me at the poster if you want to see how this guidance idea improves on spectral fidelity on the Carnatic vocal separation. Yeah, we also perform some perceptual experiments, which are really important when you work on generative audio separation, as we have seen in previous presentations. So thank you very much. See you later.
Thank you. Next, we have perceptual errors in music source separation, looking beyond SDR averages. Presented by Saujya Sakar.
Hello, everyone. So I'm here to talk a bit about the boring numbers previously mentioned. So this work is called Perceptual Errors in Music Source Separation, and it presents an analysis of a listening study that we conducted in August 2024 at C4TM during my postdoc. This work was done with my colleagues Victoria Mumjian, Emmanuel Benetos, Mark Sandler, and Basil Woods, who was from AudioStrip. So music source separation systems are usually compared using average SDR, but how do we compare models across different tasks, such as guitar separation or vocal separation? We are now used to seeing vocal separation systems perform in the range of 10 to 13 dB SDR, but does that imply a 6 dB SDR model for guitars is bad? Even comparing separation models for the same task is challenging, as different architectures may have very different performance characteristics. For example, some models might have very clean separations at the expense of spectral degradation, while others might preserve the timbral integrity at the expense of some low-level bleed. Only using a single average SDR score makes it difficult to have a more nuanced comparison between such models. These are the details that we kind of wanted to understand better to see how well does SDR capture these nuances in separation performance. So we focused on 3 tasks. First, 6-stem separation of music into vocal space, drums, guitars, keys, and others. Second was lead and backing vocal separation. And third was stuff from my PhD, which is timbre-agnostic duet separation for vocal harmonies and chamber ensemble instruments. So to evaluate how these models perform, we conducted a listening study with 56 participants from the ISMIR community. Participants were asked to rate the performance of these source separation results without being presented the ground truth, which is similar to the experience of a typical user of source separation, as we assume that they're using source separation because they don't have the sources We asked our participants to first provide a rating for how difficult do they believe the separation task is, given the input mixture and the target instrument label. We then asked the user to listen to one of our separated outputs, which were from 5 different models, and asked them to rate how good do they think the separation sounds. In total, the study had 47 input clips and 104 separations, some of which were cherry-picked examples of low SDR or bad perceptual quality. So what do the instrument-wise averages say? When we look at the averages, we find limited but insightful relationships still. We find that input SNR does not correlate with difficulty ratings. However, we did find that stems that are harmonically related to each other tend to be perceived as more difficult to be separated than others. But while comparing quality ratings and output SDR, at first glance it does appear that they correlate very well. But what if we look beyond the averages? Looking at the individual examples reveals much more. We find that SDR and quality ratings do align linearly, but things start looking a bit random below 7 dB SDR. Categorizing these bad examples based on error types starts showing some patterns. We classify examples with distinct failures into 6 error types: bleed, spectral degradation, crossover swaps, misclassifications, noise, and unison bleed. In fact, depending on the type of error, a clip with -5 dB SDR may have better perceptual ratings than an example with 10 dB SDR. We observe that different error types have very different impacts on their perceptual quality. Some errors like swaps, misclassifications, and noise seem to break away from the linear relationship between SDR and perceptual quality, while errors like noise are understandably rated very poorly regardless of the SDR. Other error types like source swaps don't seem to affect perceptual ratings as much. This results in their quality scores being much higher than the SDR would suggest. There are further intricate relationships in these deviations based on instrument type and the musical context in which the separation is performed. Do drop by the poster if you're interested, and we can explore how these perceptual errors can be, in fact, utilized to figure out how we can make source separation models work better for our purposes. Thank you.
Thank you. Next, we have bar-wise section boundary detection in symbolic music using convolutional neural networks, presented by Omar Aldi.
Thank you. It's a pleasure to be here. I'm Omar from the Technical University of Munich, and I'll be presenting our work, bar-wise section boundary detection in symbolic music using convolutional neural networks. This was a collaborative effort with Martin Melandro from Sam Houston State University. The aim of this work was to introduce a method for performing section boundary classification on symbolic music for chorus-level section boundaries, for example, between a verse and a chorus, without having to rely on using off-the-shelf audio methods by synthesizing the MIDI to audio first. And to this end, we also set out to provide a large-scale human-annotated MIDI dataset for MSA. To motivate our work, I'll start by quoting the paper, What is Missing in Deep Music Generation? A Study of Repetition and Structure in Popular Music from ISMIR 2022, which states, we need a better understanding of repetition if we want machines to compose music in a more human way. In this work, Diane, their colleague, identified relationships between rhythm, pitch, harmony, and structure. For example, being at the end of a section or a phrase, resulting in a different probability distribution over the next possible chord. And this leads us to the gap with generative music. So studies on generative symbolic models, for example, the MIDI infilling model by my co-author, Martin, composer's assistant, have identified models' tendency to generate repetitive or meandering phrases. So we think that structure-aware symbolic music generation might be valuable in alleviating this problem. This paper doesn't deal with symbolic music generation itself, but tries to address the lack of methods for performing MSA directly on MIDI. And specifically, we focus on the simpler task of section boundary detection, which aims to identify points where a transition occurs between two such sections. In audio, this is typically phrased as a binary classification task over spectrogram frames. And as I hinted towards in the beginning, a naive way of going about this might be to synthesize audio from the symbolic data and work with audio algorithms directly. But this, as you can imagine, this doesn't work too well. So instead, we transform the symbolic data to a piano roll representation and pass that to our model directly. The piano roll representation collapses all MIDI tracks onto one, which loses the instrumentation information. So to provide the model with this information, we apply an encoding scheme, where we add distinct overtones for each instrument onto the piano roll. This is the overview of our method. Following previous methods on audio, we formulate the problem as a binary classification task on fixed size patches of music. So given a MIDI file, we extract time, pitch, duration, velocity, and program information and compute our piano roll representation. And we then crop fixed size overlapping patches, and at training and inference time, the network processes each patch independently and predicts the probability of a boundary being present at the patch center. Sorry, that was a lot of P's. We train and evaluate our method on a new dataset, which we propose for MIDI MSA, called the segmented lock MIDI subset. And we collected this data by going through the unlabeled lock MIDI dataset and examining marker events that were placed by the original file authors. And we listened, and when we found the markers to represent reasonable segmentations, we included those examples. And in total, our dataset contains 6,134 MIDI files, which compares well to similar popular datasets from the audio domain. To conclude, our work proposes a first general-purpose method for symbolic section boundary classification at coarse timescales, and significantly improves over training and applying existing audio methods on audio synthesized for MIDI. And in future work, we aim to expand the SLMS dataset by performing manual corrections, including functional labels, so moving beyond just boundary detection, and exploring alternative model architectures, so for example, moving away from classification over independent fixed-size patches and performing large context sequence-to-sequence classification instead, like is done in more recent audio MSA work like the all-in-one paper, or the work presented yesterday in simple and effective semantic SOG segmentation. If this sounds interesting to you, please check out our code and dataset and come talk to me at the poster. Thank you.
Thank you. Next, we have collaborative playlists around the world, a cross-cultural user study, presented by Jinha Li and Xiao Hu.
Good morning, everyone. I'm happy to present our work on collaborative playlist with my colleague Xiao Hu. In this paper, we study users of collaborative playlists, or CPs, and they're defined as a list of songs that have multiple users putting together songs in this digital platform. And it's an increasingly popular feature in a lot of different systems. So in our previous work, we learned that users engage in CPs for three main purposes, which were practical, cognitive, and social. And we also identified two connotations, which were utility and orientation. And people also reported that CPs help them feel that they can better connect with others through music. But interestingly, while engaging with CPs is fun and meaningful, some interactions can feel uncomfortable because of the sense of ownership. So for instance, if you and I had a CP together and you deleted my BTS song, then we would need to have a conversation about it. So many of these studies, including our own, actually tells us something about the CP users, but they're predominantly based on North American samples. And this gap led to our current study, which is a study where we explore these dynamics with users from 4 different cultures: Hong Kong, South Korea, Quebec, and US. So we had 2 research questions. First, for what purposes do people in different cultures engage in CPs? And second, how do people in different cultures perceive and experience the outcome of CP usage?
Well, for the first research question, what we found was that the 3 purposes of engaging in CPs all emerged across all the cultures. There are some similarities among the cultures. For example, compared to interested non-users, all the users from the 4 samples mentioned less on cognitive purposes, which is about finding new music and to understand the other's taste. But there are also differences across the 4 cultures. For example, as you can see here, for the practical purposes, our Korean participants actually mentioned a lot less than other participants. For our RQ2, which is the outcome of CPs, all the 4 cultural participants agreed that the CPs was helpful for them to diversify their music libraries and increase the ways in which they discover music. They also agreed that the CPs the music helps them connect with others. But the participants from the United States actually agreed more than other participants. So the major takeaway from our result is that for both the purpose and the outcome of engaging in CPs, all the participants from the 4 cultures have some similarities and some differences. And the differences actually are not depending on the geographic proximity, as many of you might think. And also it's not dependent on the usual perception of the Western versus Eastern. What we actually found was that the participants in Hong Kong and Quebec were more similar, and also those in Korea and those in US were more similar.
So in our future work, we plan to continue this work with larger samples and doing more granular within culture stratification. And we also want to do a follow-up study using interviews and ethnography to observe real-world usage. So here's the information for the ISMIR paper, which we invite you to read. And please come see us at the poster session. Thank you.
Thank you. The last paper, we have the AI music arms race on the detection of AI-generated music, presented by Laura Claus-Vida.
Hello, thank you for the introduction. Hi everyone, I'm Laura and I'm here to present our work that I did together with my co-authors Bob Sturm, Luca Cassini and David Dalmazzo. And I'm going to be talking a bit about the AI music arms race. So I guess many of you here know, but there now exists a lot of services that allow users to generate music. Here are a few of them. These technologies are becoming more capable of creating music that can compete with that made by humans, and at scales never seen before. And the number of companies offering such services just keeps increasing. As the quality of this music rises, concerns grow about how to differentiate AI-generated music from human-made music, with implications for content identification, copyright enforcement, and music recommending systems. So what did we do? Well, we explored the detection of AI-generated music by assembling and studying a large data set of music audio recordings from 2 prominent AI music companies who are present here at ISMIR, Suno and Udio. And we collect 10,000 audio recordings from each service, from public playlists of new releases, and we then use a subset of 10,000 recordings from the million-song dataset as a human-made music comparison. We then extract and compare music descriptors for each collection, both low and mid-level features, as well as learn deep embeddings such as clap. We can then use visualization tools such as UMAP, and we see that the recordings from Udio seem to be closer to the million-song dataset ones than Suno is. And we also get to similar conclusions when we compare the extracted music descriptors. We then create 3 AI music detection systems operating on clap embeddings using hierarchical classification strategy based on the local classifier per node approach, where basically at each node we use either support vector machines, random forest, or 5 nearest neighbor classifiers. And we do that because we wanted to see not only if the classifiers can detect AI versus non-AI music, but we also wanted to investigate if they're better at just identifying specific sources. We compared the performance of our systems to the system spectra proposed by Raman et al. And we also compared it to the commercial IRCAM Amplify AI music detector, which for now it seems to be the state of the art. We see how our relatively simple detectors perform similarly to the commercial music detector, and the spectrum model performed slightly worse, and we believe we found the reason why. Come to the poster to see more details. But we find several vulnerabilities in the detectors. We go a lot in detail in the journal article, but for example, we found that it's easy to fool the best detector, the Earcom Amplify. You just need to resample or downsample the audio recordings to 25 kilohertz, and then basically it will misflag. First of all, like it will completely miss Suno audio recordings, so it will not flag them as AI, some of the audio ones, and actually also it will flag human-made music as AI sometimes as well. But yeah, some final remarks. So AI music detection works. It's very, very easy to get good accuracy, but it's not that simple. I mean, our results are sort of like empirically proving the work of Darius at the beginning. So basically what we find is that there seems to be some artifacts in the higher frequencies in these audios generated by the systems. But we also see that this is an AI music arms race. So we will develop detectors, new systems will come. So we just need to evolve with it. But yeah, we have released all of our code. You can find it on GitHub and then the ISMIR article as well. But please come, let's chat. I love to talk about what we found. So thank you.
Thank you. So this concludes the oral session 7 and all oral session of ISMIR 2025. Please now go enjoy your coffee and more discussion in the poster session. Thank you.